Welcome, my name is Suraj. I'm a GSI for Data 100 this fall 2018 semester, and in this series of videos we're going to be walking through the fall 2017 midterm from this course. A couple quick notes. One, we'll be skipping a few problems, namely 19 and 20 and 25, 26, and 27 because they're out of the scope from what we're covering in this semester. The reason for that is because we've shuffled around some of the topics, bringing some of the topics that were usually covered later in the course closer to the beginning. And so another side effect of that is that the midterm will likely be more challenging than this fall 2017 midterm that you're seeing, because we've moved some of the more difficult concepts up from the end of the course to before the midterm. In this video, we're only going to go over the first section, which talks about data generation and probability samples. So let's get into it. In the first question, a political scientist is interested in answering a question about a country that's broken up into 3 states with 10,000, 20,000, 30,000 voting adults in each. And in each state, we randomly sample 25 for the first, 50 from the second, and 75 from the third. The type of sampling plan this is stratified sampling, right? This fits directly to the definition of what a stratified sample is. In a stratified sample, we somehow create clusters or strata of our data, right? And so here our strata are the states, and within each strata, we do some sort of simple random sample. And that's exactly what we're doing in this question, so this is a stratified sample. In problem 2, we're told that we have a deck of 26 cards labeled A through Z. We shuffle it and we want to find the probability that the third card is a C. Okay? And a lot of people, when seeing this question, might jump to the third answer, right? Well, it's the probability that the first one's not a C times the probability that the second one is not a C times the probability that the third one is a C, right? However, that's actually not correct. The correct answer is 1/26th, right? Because the probability that a C ends up in any one of the 26 positions is equally likely, right? The probability that we have a C in the 10th spot is the same as the probability we have a C in the 26th spot, is the same as the probability we have a C in the 3rd spot. They're all equally likely, and they're all 1 in 26. In problem 3, we suppose some guy named Sam visits your store to buy some items. He buys toothpaste for $2, 0.5 of the time, and he buys a toothbrush for $1, 0.1 of the time. And we want the expectation for the amount of money that Sam spends. Okay? We can break up this expectation into 2 parts, right? We can say the total amount of money he spends, X, is equal to the amount he spends on the toothpaste, which I'll call P, and the amount of money he spends on the toothbrush, which I'll call B. So the expectation of X is equal to the expectation of P plus B. But since expectation is always linear, I can write this as the expectation of P plus the expectation of B. Now the expectation of how much he spends on the toothpaste, well, he either spends $2 with probability 0.5 or $0 also with probability 0.5. But the $0 doesn't really contribute to our sum. The expectation of how much he spends on the toothbrush, well, he spends $1 with probability 0.1, and he spends $0 with probability 0.9. But again, the 0 term doesn't contribute to our sum. So now we're left with 2 times 0.5 plus 1 times 0.1, which is 1 plus 0.1, which is precisely 1.1, which tells us the expectation of how much he spends is $1.10. In problem 4, we're given some coin that lands heads with probability 0.8, and we want to find the variance of the proportion of times, so not the number of times, but the proportion, which is slightly different, that that coin lands tails out of 100 flips. So let's just pretend for now that P is equal to 0.2, right? Because if the probability that the coin is heads is 0.8, the probability that it's tails is 0.2, right? So what we can do is define this indicator random variable that's equal to 1 if flip I is tails and 0 otherwise, right? And of course it's 1 with probability 0.2, and it's 0 with probability 0.8. Cool. Then we notice that the sum going from I is equal 1 to 100 is the number of flips that are tails. But x is defined to be the proportion of tails, or a proportion of flips that are tails, not the number of tails themselves. That means x can be written as 1 over 100 times the number of flips that were tails. Right? Because to find a proportion, it's essentially a percentage, we divide by 100. So now we want to find the variance of x. Well, that's just the variance of 1 over 100 times the sum of all xi's. And I'm omitting the i's equal 1 to 100 notation just for the sake of brevity. The first variance rule we'll use is the fact that the variance of ax is equal to a squared times the variance of x. Okay, that means I can write this as 1 over 100 squared times the variance of this sum. The next fact we'll use is that the variance of x plus y is equal to the variance of x plus the variance of y when x and y are independent. In this case, are all of the xi's independent? Yes, because individual coin flips are assumed to be independent. So I can write this as 1 over 100 squared times the sum of all of these variances. But since each coin flip is identical, all of these variances will be the same. So that's 100 terms that look the exact same, right? Because again, this sum is supposed to be going from 1 to 100 times the variance of x1. Okay, it doesn't matter that I chose x1. I could have put x23 if I wanted. Now, our question is, what is the variance of one of these flips, right? Well, so first, the question is, what is the expectation of a flip? It's 0.2. And we get that because it's 1 with probability 0.2, right? This random variable up here is 1 if flip I is tails. And it's 0 with the remaining probability, and that's just 0.2. So the variance of xi is the expectation of xi minus 0.2 squared. Right? So this term is equal to, with probability 0.2, xi is equal to 1. So it's 0.2 times 1 minus 0.2 squared. And with probability 0.8, xi is equal to 0. Right? And you can do the algebra here, and you end up finding that this quantity is equal to 0.2 times 0.8. If you've taken a probability course in the past, such as CS70, Prob 140, EE 126, you will have recognized all of these steps from before as being the variance of a binomial distribution, or this specifically what we just did as being the variance of a Bernoulli distribution. But this question sort of asked us to derive that, so that's why we went into a little more detail. Anyways, the variance of any one of these flips is 0.2 times 0.8. So we write this as variance of x1 over 100 because the 100s cancel. And we're left with 0.2 times 0.8 over 100, which is 0.16 over 100, which is 0.0016, which is one of the options. Lastly, we'll look at number 5. We're given that a small town has 5 houses with the following people living in each house, yada, yada, yada. Suppose we take a cluster sample of 2 houses without replacement. Okay, so it's equivalent to choosing one house and then choosing the next house. And we want the probability that Kim and Lars are in the sample. So it's important to notice that Kim and Lars happen to be in the same house. So this question boils down to, what is the probability that this 5th house is chosen? So there's 2 ways it could happen. Either with probability 1 over 5, it's the first house that's chosen, or it's the second house that it's chosen, right? So if it's the first house, the probability is 1 over 5, But if it's the second house, that means it's not the first house with probability 4 over 5. And then it's the second house with 1 over 4. Because once the first house is chosen, there's only 4 houses left. And the probability that the fifth house was chosen in that case is 1 over 4. But this happens to simplify to 2/5, which is one of the answers. Cool. Part 2 asks us to find the probability that Kim, Abe, and Ben are all in the sample. Looking at the houses again, Kim is in a house on her own, and Abe and Ben are in the first house. So this narrows down to the probability that we choose the first house and the fifth house. Right? So either we can choose Kim's first, then the house with Abe and Ben, or we choose the Abe and Ben house first, then the house with Kim. Right? The probability that we choose Kim's house first is 1/5. The probability that we choose Abe and Ben's house next is 1/4. So that's 1 over 20. The probability that we choose Abe and Ben's house first is 1/5. And then Kim's is 1/4. So that's 1 over 20. So the total probability is 1/10. Because it's either the first case or the second. So we add those two things. So we have 1 over 10. Another perhaps more straightforward way of looking at this is we know that there's 5 houses and we're choosing 2 of them. That means there's 5 choose 2 ways to pick 2 of these houses. And essentially we're finding the probability that we choose the first house and the fifth house. Well, that's one of our 5 choose 2 possibilities. So the probability should be 1 over 5 choose 2, but 5 choose 2 is 10. So we have 1 over 10 again. In the last part, we're asked to find the probability that Kim and Dan are in the sample. Looking at the houses again, this is essentially the same problem as the last one, but instead of looking at the first and fifth houses, we're looking at the second and fifth. So the probability should be the exact same. So it's the same as the chance that Kim, Abe, and Ben are in the sample. It's not the same probability as the one where Kim and Lars are in the sample, because Kim and Lars are in the same house. So that's a slightly different question. This is the same as trying to find the probability of choosing 2 different specific houses. And that ends our section on data generation and probability samples.